to my channel. In my last video, right, I dealt with combinatorial chemistry, right, initial things of combinatorial chemistry. So now we'll do, in continuation to our previous last topic and all, we have not finished yet, right? Okay, let us deal with because I think that in the last video I talked about the support material and all, right? So now we'll move to the next one, that is linker, right? So linkers, it is another important things and all, right? Linker. As I said, the support material is found to be inert in nature. That means we are not expecting that the support material should provide a functional group, right? Because the thing is that as we are using a support material, suppose this is found to be the support material, right? And I am going to introduce what multiple reagents. Assume that we are in the age of 1990s, right? Late 90s or early 90s, right? We are making, suppose we are going to make what? Peptides, right? So suppose we have with us AA1, AA2, AA3. 3 amino acids are there. Let it be anything like glycine, alanine and valine, right? So all are found to be neutral amino acid, right? Chalo. So now what next? So amino acid means what? Amino acid means it should have a C terminal and N terminal, right? If I just try to figure it out, the simplest of all, that is glycine, right? So how it looks like H3N plus CH2, and then finally we have a C terminal, that is O minus. I have just presented it in the form of a zwitterion, right? Zwitterion, CO minus and S3 plus, right? Okay. So we have a C terminal, we have a N terminal, right? Which I'm just trying to merge alanine. Now before merging, I should fix the starting material because I am in the process of what? Making glycyl, alanine, valine. This is found to be the sequence, right? Glycyl, alanine, valine, right? So glycine is found to be the starting material here. It's not that कि okay चलो कहीं से भी हम लोग ये तीनों को एक साथ मिला लेंगे उसके बाद इसके ऊपर डाल देंगे, ऐसा तो नहीं है ना. ये सपोर्ट मटेरियल है, मतलब आपको एक के बाद एक इस यहाँ पे डालना पड़ेगा, ठीक ना? तो चलो डाल दिया, मतलब this should not float on the support material. The support material should hold the starting material in such a way so that it can accept the subsequent reagents as well. Okay, without affecting the reaction condition as well as the reaction as well as the intermediate and formation of the intermediate. This should be held by this support material in a formidable way, in a robust way, right? So that means by means of a formation, by means of making a particular bond only, this can have an access to this particular solid support, right? So that means we have to derivatize the solid support, right? We have to derivatize the solid support. That is why sometimes they are using the term called linker with active functional group. That means the linker is found to be a big molecule. Suppose we have multiple phenyl rings, they are connected by means of alkyl or alkoxy, but we are least concerned about this portion of the linker. We are concerned about the functional group that it is holding. That means the functional group which is involved in accepting what? The first starting material, so that the subsequent process will not get interrupted. Got my point? Chalo. Now, so likewise, we are not supposed to, I am not supposed to, draw the entire structure of various linkers which are used. Rather, I should mention here the functional group that each and every linker is holding, and the kind of starting material which they can accept, and the final product which they are likely to release rather, right? Chalo. So that means we have several linkers, okay, that are there, several linkers starting from Wang resin, right? Wang resin, and then as now why resin? You may raise a question that why resin? Why not resin? Because we are fixing the functional group, we are fixing the linker to the resin. No, that is why, as it is attached to the resin, this is not found to be the any chemical. This is the scientist, okay, who discovered the linker, right? So Wang resin means the functional group should have a connection with the solid support. So that is why, as it is attached to that particular support, that is why I am using term Wang resin. So we have few more linkers. These are the examples of linkers. So Wang resin, then your Barlow's resin, then your ring resin, we have a dihydropyridine resin, We have stressless linker as well. Right? So these are the few, the few I have put, I have just written here, right? So let us just deal with that, right? And the selection depends on what? The starting material which you are going to introduce in the system, and the final product which you are desiring. Got my point? So these are the two criteria. Criteria for what? Criteria for selection, right? So the selection depends on what? The starting material which you are going to introduce. At the same time, the final product which you are desiring, right? Chalo. So now let us deal with that what are the functional groups, what are the principal active functional groups that each and every resin of the linker they are holding, right? And with which they are growing the affinity towards the starting material, right? Chalo. So it is the Wang resin that is holding a hydroxyl. So the active functional group present in the Wang resin is found to be the hydroxyl group. Chalo. That means it is the hydroxyl that is involved in the initial interaction with the starting material, right? The first amino acid, the hypothetical peptide that we have developed, that is glycyl, alanine, valine, right? Chalo. So Wang resin, hydroxyl. There was some problem with the Wang resin. What was the problem? See, in Wang resin, okay, though we can make so many peptides and all, but sometimes they observe that the first amino acid, that means the one which which is directly connected to this particular hydroxyl, right? Okay, sometimes it undergoes racemization. This was the problem, right? So that means it is the first amino acid. Out of this attraction, out of this interaction, out of this formation, sometimes it may undergo racemization. So this is found to be one of the problem. Once it got racemized, then again finally the product which you are going to get, right? Then you have to go for what? Enantiomeric separation. It's a racemic mixture, right? 50-50 is there, right? But we are not expecting that 50-50 both are found to be active. If the D is active, then you have to separate the D from the L, right? Or from the DL rather, right? Chalo. So now Wang resin, the problem was there that the first amino acid which is linked to this hydroxyl, that will undergo racemization, and that is why Barlow's resin came into the picture, right? Barlow's resin. So what is the Barlow's resin? Barlow's resin is basically, it's a trityl resin. Trityl. Trityl means what? Trityl means it is something like this. So this is trityl, right? So this is found to be the feature of trityl, Barlow's resin. Now once we are using this particular resin, we can readily overcome the problem which we encountered while dealing with Wang resin. That was, we can avoid the racemization of the first amino acid. I am not telling that each and every amino acids which are found to be the part and parcel of the entire peptide chain, right? All are undergoing racemization. Is the first amino acid, we are not expecting, not even a single amino acid will undergo racemization. So that is why we can straightway avoid the chance of chances of what this racemization problem, right? Chalo. So we are done with Barlow's resin. Now the another one, that is ring resin. The active functional group that the ring resin is holding is what? Is amino NH2. As I told that, I am not going after making or drawing the entire structure. Why? Because the entire structure is not having any connection in my discussion, because I should stick to that particular functional group which is involved, which is participating in the process of accepting the starting material which is used in combinatorial or parallel synthesis. Got my point? Chalo. Now, so the ring resin, it is holding an amino group, right? So the active functional group that is present in the ring resin is found to be amino group. I'll come to it, what kind of starting material that we can involve or that we can introduce into that particular event and all, and what kind of product that we are supposed to get, right? Chalo. Now coming to this dihydropyridine, so how it looks? Dihydropyridine is found to be something like this. As I said, pyridine, so it should be something like this, right? It should be something like this, right? So this is found to be dihydropyridine. Now the next one, now why it is dihydropyridine? Why not trihydropyridine? That is why you're supposed to write it in that way. One point has to be considered as H, right? The moment you are just, and they definitely you have to put the locant number as well. The locant number with capital H and later on dihydropyridine. Okay. With that you are done with the IUPAC naming of what? The pyridine in this form. You are not calling it as trihydropyridine. That means something H then dihydropyridine. Right? So once you are putting H means you are left with another 2 points, right? The 2 points are found to be hydrogenated. So that is why you are just calling it as dihydropyridine. Something capital H dihydropyridine, right? So with that we are done with dihydropyridine and sometimes stressless linker. That means nowhere you can trace the the portion of that particular or rather you cannot figure out the functional group which is involved, right? Stressless linker, right? Stressless linker. Now let us deal with this because and mostly these are the resins, these are the linkers which are found to be of huge use rather. Okay, they are having immense importance in the field of combinatorial chemistry, especially the peptide synthesis, right? Yes, though in non-peptide also they are used, they are of use rather, but in mostly the peptide synthesis, yes, these three, 1, 2, 3. Wang resin, ring resin, dihydropyridine. Okay, they are of huge use, it seems, right? Okay. Now let us see that what kind of starting material with which we can start up the reaction when we are after selecting Wang resin, right? So when we are going to deal with Wang resin, so what kind of starting material which we can introduce into the system? As I said, Wang resin. Let me just put the acronym for it. I'll just write WR in short, right? Okay, you can readily trace what WR stands for. Wang resin, right? Okay, chalo. Wang resin. Now, so Wang resin, the functional group that is holding is what? Hydroxyl. Now let us see what kind of starting material that it can accept, right? Okay, because it is the functional group that will interact with the functional group of the starting material, so that there is a formation of another newly formed functional group, right? Okay, I'll come into it. Hydroxyl. We all know that hydroxyl, while dealing with or while reacting with carboxylic group, there is a formation of an ester, right? So that means, and we all know that at the initial stage, people were very much involved in making the peptides and all, and we know peptides is nothing but a combination of so many amino acids, right? So that means an amino acids are having C-terminal and N-terminal. So we can straightway say that hydroxylase can interact with what? COOH. C-terminal, right? So that means a carboxylic or carboxylated compounds can be introduced or can be linked with what? This particular linker. That means Wang resin, the starting material that can be given is should hold a carboxylic group, and what kind of newly formed functional group that we can expect here? Like O, C, double bond O. And this O is connected to a bed. So this is found to be the resin bed. This is found to be the resin bed. It can be of anything, right? As I said in my last video. So this is found to be the resin bed, RB. So this is found to be the oxygen coming from the linker, and this is found to be the C double bond O coming from the starting material, right? So with that we are done. So now the thing is the carboxylate, we are left with what? CH2 and then finally NH2. I am not supposed to write here NH2. Instead I will just put it a protecting group here, PG. Why? That I will discuss, okay, in a few moments, right? Okay, so this is about your Wang resin. Now coming to ring resin, right? If I just change it to ring resin, the active functional group is found to be amino. So what kind of starting material that it can accept, that it can react with? The starting material should have a carboxylic group with which it can form what? Right? Resin bed NHCO. And the kind of product that it can release it what? And here the rest. That means it can accept a carboxylic group, it can release an amide. That means a portion of this amino should get released. So that means Wang resin, it can accept a carboxylic, it can release a carboxylic. Ring resin, it can, by virtue of its amino group, it can accept a carboxylic group or carboxylated compound, and it can release an amide. Now coming to this dihydropyridine, in case of dihydropyridine, what kind of functional group that you can introduce, right? Or with which it can interact rather. So this is found to be the dihydropyridine, right? Dihydropyridine. Let us see that what kind of starting material. Now we all know that this particular pi bond can get broken. Okay, it can participate in accepting a particular and gets shifted rather. Can I write in this way? OR. Suppose ki I am just trying to introduce a ROH here. So what this ROH will do? What this ROH will do? This ROH will get fixed with this, fixed to this. How? By virtue of this. Right? And subsequently what will happen? Subsequently things will get changed, right? Okay. And finally I can alter the, the R. R can be further modified. Suppose the R is found to be CH2, CH3. I can make it like CH2, CH2, CH3 like this, or even I can make it some other form. I can give some other form as well, right? So likewise, it can accept ROH, and the kind of functional group that it can release it, same ROH only. The moment ROH will get released, again it will regain the dihydropyridine form. Right? So this is all about here, the various linkers and the kind of functional group with which they are interacting, right? Okay. Now, in my today's proceedings, or in this particular topic, I told that NH, you should not leave it as such. You should not leave it as such. Now as I told that the NH, right? Because still we are in the 1990s, right? That means we are in the process of making the peptides and all, right? And we know that peptide is nothing but the formation of CONH. One amino acid should provide the C terminal, the other will come with this N terminal, and there is a mutual understanding so that there is a formation of a CONH, right? So that means and once the C terminal and N terminal is engaged, that means the other C terminal is found to be free, right? Okay. There is no such problem will occur when C terminal is found to be free. But the N terminal should most of the time should remain what? Should remain protected, right? Protected. Why? Now let us come to the third requirements. That is, so we are done with the solid support. We are done with the linkers, with active functional groups. We are done with we are going to do deal with this protecting groups, right? Why protecting groups are used, right? Suppose here I am just bringing two amino acids. So one is found to be okay. It's for my convenience. I'll just make it in this form, right? Right. Okay. So we have with us here two amino acids. Both are found to be glycine. Both are found to be glycine, right? Okay. Now, as both are found to be glycine, all I want is the N terminal. Suppose this is found to be the A and this is found to be the B, right? All I want is the N terminal of A should interact with the C terminal of B. This is my projection. This is my design. This is my requirement, right? I want the dipeptide, and that too where the N terminal of A should form a peptide linkage with the C terminal of B. But what happened? As I have just left it unprotected, there may be a chance that the N terminal of B has reacted with the C terminal of C. Now can we say that as per our projection, as per our design, we got the product? No. Why it happened? It is because we have left some active functional groups unprotected. So that means, and this can readily avoid it. This can be readily overcome the moment you are protecting either of the functional group. Mostly the N terminal, right? And for that, the functional groups, or rather, I should not say, the functional group should be protected with protecting agent, right? So what are the protecting agents? Now, so the protecting agents which we are using, basically they are found to be VOC, they can be FMOC, they can be NVOC, they can be even benzyl, they can be tertiary butyl as well. Tertiary butyl as well, right? So these are the various protecting groups which are of use till now. In conventional, in combinatorial, in both the cases, either of the cases. If you are dealing with normal conventional synthesis of peptides, there also you will find what? The protecting groups or protecting agents, right? Okay, you can find, right? Chalo. So what is the BOC? What is the FMOC? BOC means butyl oxycarbonyl. Butyl oxycarbonyl. That means H9C4 C double bond O CO. I should not write in this way. As I said, butyl oxycarbonyl. This found to be like this. FMOC. What is that FMOC? FMOC is fluorinyl methoxycarbonyl. So here fluorine means it's not the atom fluorine. It's not RINE. It's RENE. Fluorine. FLUORENE. Fluorine. Fluorine is a tricyclic system. Tricyclic system means it's like this. What my point? So this is your fluorine, right? Okay, this is your fluorine. Fluorinyl. So as I said, fluorinyl methoxy. Methoxy means CO. Then carbonyl. What my point? So this is FMOC. NVOC means nitroveratril oxy. Nitroveratril oxycarbonyl. So what is that nitroveratril? We all know about nitroveratril. Why? Because in nitroveratril, you might have those who are in their third year. Those who are in their third year, they might have gone through the structure of papaverine, right? In the structure of papaverine, you might have noticed the veratril group. That means a phenyl with 2-methoxy, both ortho to each other. Got my point? This is veratril. Nitroveratril, that means in that benzene another nitro group is there, and then another point we have a oxy, nitroveratril oxycarbonyl, like this, right? So we have a nitro, we have methoxy, and this all the things they are being this is the phenyl ring which is holding. All are being held by a centrally placed phenyl ring. So this is found to be nitroveratril oxy. These are of less importance, benzyl and tertiary butyl. So they are of use. BOC, that is BOC, butyl oxycarbonyl. So all are meant for what? Or most of them are meant for what? Basically the NH, the nitro group, the N terminal of amino acid, which is protected with what? N terminal of, it can be of amino acid, it can be of any other amino group. The FMOC, NH FMOC, BOC, BOC, they are of use, right? So now we are done with what? The protecting group, NH-FMOC. Suppose I am just writing NH-FMOC. And the protecting group has to be chosen in such a way so that the protecting group will not alter the functionality or the property of the group with which the group which it is protecting. What my point? Suppose it is linked to this amino. No longer, it should not alter the property, the basic property or the native property of this amino. The selection should be done in such a manner so that it cannot interfere in the process of altering the property, right? So that everything will get, will be lost, rather, right? Or will get affected, I should say. Chalo. So FMOC, BOC. So now the moment you are adding protecting group, that means you should have what? You should have a deprotecting agent as well. The deprotection has to be done, right? Usually the deprotecting agents that are used in combinatorial chemistry, they are found to be TFA. They are found to be TFA, HF, that is trifluoroacetic acid. Sometimes they are using piperidine as well. Piperidine as well, right? Okay, but HF less used, right? TFA, piperidine more used, because the use of HF, okay, it requires extreme caution, because HF, hydrofluoric acid, is such an acid, right, which is having a glass dissolving ability. Okay, if you just hold or take this hydrofluoric acid in your raw hand, it may happen that the hand with which you are holding this HF in the raw hand, the hand may get amputated. It had happened to a particular driver, okay, who unknowingly taken this HF, okay, in a cotton swag, right, and after that, while mopping this glass window, thinking that probably the HF can remove the scratch which built in on that glass window, right? Okay, suddenly he found that the glass window got dissolved, and after a span of 1 month, okay, the doctors, the owner of that particular car found the driver, his hand was amputated. You just imagine that HF is such an acid which can dissolve glass, right? Okay, glass. So that means that much corrosive it is. So extreme caution has to be taken while using HF. But this kind of caution cannot be, you are not supposed to, take this kind of caution while dealing with TFA as well as piperidine, because in milder condition, the piperidine, TFA, they are used. But let me tell you one thing, in extreme condition, sometimes in extreme condition and during the process of separating the compound which has been formed on the platform, that means while separating the compound from the solid support, HF, TFA, they are of use, right? In extreme condition, HF can be used for the separation of what? Separation of the final component from the support material, because we are not expecting the final compound should have with it the starting material. Okay, so now with that we are done with the requirements. Now on the basis of our requirements, right, if we just try to shape it up, how it looks, so we have a resin bit. Let us just do like this. We have a resin bit, right, spherical in nature, and we have a linker which is holding the active functional group, suppose KNH, and I have utilized the C terminal of an amino acid. So what I can expect here, CH2, NH, FMOC, NH, FMOC. So I need to add another amino acid because I have to run the show, right, for a particular period of time, or as per my design and all, right. So what next? Initially the FMOC has to be deprotected, and for that certain suitable regions are there. Like you have with you the piperidine as well, you can use that one, right, for the removal of FMOC and all. So piperidine, while using the piperidine removed or deprotect this N terminal so that the next amino acid can access the N terminal, right? You are bringing the next amino acid A to merge it with this. Definitely we'll get like this, CO, CH2, again NH, FMOC, right? And then finally, once you are done with this making of this peptide, then we have to separate separate the entire compound from this bit. Use this HF or TFA. They will separate them, right? Now the beauty of this is, if the resin bit can be used with great care, you can reuse the resin bit as well. Why? Because the resin bit itself is inert in nature, and one thing you should keep it in your mind, the resin bit should have the quality to swell. If it is not swell in a proper way, you cannot access each and every functional group provided by the linker. Why? Because the linker is distributed all along the resin bit. So if it is not swell properly, so what will happen? Definitely the starting material cannot access each and every functional group provided by the linker in a proper way. That means it may lose few contacts, so that the yield will get affected. That means in order to access each and every functional group of the linker, as the functional group of the linker is distributed all along the resin bed, that means the core need to be unfolded. The core of the resin bed need to be unfolded so that the functional group will get exposed. The functional group of what? the functional group of the linker will get exposed and the subsequent reagents can access the functional groups. Got my point? So with that we are done with the basic requirement of what? Combinatorial chemistry. In my next video, probably I'll deal with the methods of combinatorial chemistry, right? Thank you so very much for your kind patience. Thank you.